Good afternoon and welcome to the webinar, The Future of Commercial HVAC, Directly Coupled Air Handling and System Efficiency Benefits. This event, brought to you by Appliance Design, is sponsored by Regal, featuring Marathon Motors' latest product edition, UlteMAXT Motors. I'm your moderator, Darryl Seland, Editorial Director of Appliance Design. Thanks for joining us. Before we begin the presentation, I want to provide you with a few housekeeping items. To the right of your screen, you will see a taskbar. Each icon on the taskbar is assigned to a particular element of today's webinar. If you are unsure about what an icon does, hover over the icon with your mouse and a box will pop up that tells you the function. Please find a copy of the presentation, technical support tips, and email support in the Handouts section. Please take our survey following the webinar by clicking on the survey icon in the taskbar. Next to the slides window, there is a blank questions box that allows you to type a question in the box and then hit submit to send it to us. Later in the live program, our panel will address as many questions as possible. Today's event is being recorded and archived on appliancedesign.com. All registered participants will receive an email within 1 to 2 business days that has a link to view a recording of this event. And now I'm excited to turn it over to today's first presenter, Jason Kreidler.
Good afternoon, everybody. My name is Jason Kreidler. Thank you, Darryl, for the introduction. I'm the manager of enabling technology and also a chief mechanical engineer here at Regal. I'm extremely excited for what my team has to present to you here today. I joined Regal 21 years ago, and I've spent most of my career in research and development engineering type roles, and developing different product lines to solve unique customer problems. And if there's one thing that I've always tried to focus on, it's solving unique customer problems in ways that are meaningful, simple, and elegant. And what we're going to show you today, we think checks all those criteria. Next slide, please. Okay, in this session, there are 4 key takeaways that I'd like us all to have. So probably not a test at the end, but it sure would be nice if you could come away with these 4 points in your mind. First of all, we understand that maintaining a competitive edge and keeping ahead of the upcoming energy regulations is really on the forefront of your mind. And as participants in the HVAC industry, you're looking for solutions that helps to solve these problems. And today we're going to have some discussion around directly coupled air handling and how that impacts positively your energy efficiency. And really, we always try to look beyond the obvious. UlteMAXT, the name of the motor that we'll display, is based on ulterior, and it's beyond the obvious. So UlteMAXT is where that name finds its inception. And we're going to try to explore some of the non-obvious benefits of our technology. The key takeaways. So we want you to identify the key drivers in change for the HVAC industry. So why are we changing? What's the need here? Why don't we just keep going with the current technology that we have? Second point, we want you to understand why the industry is shifting over to integrated motor fans. So again, we've got a solution that works. Why doesn't that work in the future, and what can we improve upon? The third point, we need to move to PM motors and variable speed. And PM motors, so permanent magnet motors, and in this case, a permanent magnet AC type motor. We're going to talk about some of the efficiency benefits of that and why that efficiency benefit and how that efficiency benefit helps you. And also the benefits of variable speed. So instead of just running at one fixed speed, we can run at variable speeds and talk about what that does from an efficiency standpoint from an overall system power use energy type of a situation. Fourth, we want to look at how to enable a better HVAC product with an integrated motor fan unit. So we don't want to do it the same. We don't want to do it as we've always done it. We want to do it better. We want to provide you value. We want to provide your customers value. We want to provide our end users in the building doing the maintenance and feeling the air move. That's who we want to connect with and provide value. Please go to the next slide. So I'm excited to introduce Dave Hyypio. Dave Hyypio is Chief Electronics Engineer for Regal, and Dave has been with our company for 23 years. And very creative, very well established, and very knowledgeable engineer who has clearly earned the title of Chief Electronics Engineer within Regal. Dave's career has been spent developing electronics to meet sort of niche applications. So you see a digital voltage regulator for a synchronous generator. Dave's really good at understanding niche applications, how he can affect those, and how we can improve them. Go ahead to the next slide, please. You skip the slide there. Finally, I'd like to introduce Matthew Turner. Matthew Turner comes to us, actually, he's on an assignment up here from our Australia location in Melbourne. The Australia team is really kind of the grandparents, the birth parents of the axial technology. So it was developed in Australia, really in university, and then they built a startup company, and Regal acquired that startup company through one of our acquisitions, and we've been using the axial technology to solve different problems. Matt is an accomplished engineer who started really inventing things. Here it says at the age of 7, and I think that he hasn't lost that curiosity of a child, but he's added to that curiosity a wealth of experience and technical expertise that lets him approach things in a very simple, elegant way to solve problems that are meaningful to our customers. With that, I'd like to turn it over to Dave Hyypio to start our conversation.
Thanks, Jason. I thought it would be appropriate today to begin the talk about the future of commercial HVAC by looking at the amount of energy that is consumed by this particular sector. According to the DOE stats, the commercial sector consumes 4.63 quads of electrical energy, and a quad is a quadrillion BTUs, and that is equivalent to 1,357 terawatt hours, if you can get your head around that. But that's just a boggling amount of energy, and is equal to 33% of the net electricity that's generated in the U.S. annually. So looking at commercial systems, then the HVAC systems portion of the pie within that accounts for about 10% of the energy used by the commercial sector. And then within that 10%, breaking it down further, supply and return fans make up 50% of that energy usage. So if we look at that small purple table on the slide, we see that just doing simple math and applying the electric rate, the average commercial sector electric rate of 10.5 cents per kilowatt hour, we get an energy bill of $71 billion per year. So very, very significant amount of money there, and I think just a 1.4% increase in efficiency would amount to a $1 billion savings. So just so everyone gets a magnitude of the type of potential that's here in this market. And then it's incumbent upon us to convert this power more efficiently, more intelligently, to get the work done within our world. So what is driving the change? Of course, there's government regulations. We have tax credit programs. There's a IRS code by the name of 179D, which provides a deduction of $1.80 per square foot. It's available to owners or designers of new or existing commercial buildings that meet certain ASHRAE standards. We have the Department of Energy and NEMA initiatives. And NEMA is an industry organization that initiates energy efficiency policy and advises policymakers in government, and works with coalitions of environmental, consumer, and energy efficiency organizations. And then down at the appliance and commercial level, we have things such as the Energy Star program. Energy Star was introduced by the EPA as a voluntary labeling program to identify and promote energy-efficient products. The Energy Star label is now on major appliances, office equipment, and commercial and industrial buildings and plants. Utilities are another main driver of change. Based on the previous slide with the magnitude of the amount of energy that's consumed in this sector, we have to keep in mind that the utilities have to start with 3 units of fuel energy to deliver 1 unit of electrical energy at the end use. So there's only a 33-34% efficiency rate there. So there are major savings to be had by saving the utility the need to expand their infrastructure or to increase the efficiency of loads that are already online. And of course, the environment is another big driver of this change. We're all looking for reduced emissions, and it's incumbent upon all providers of equipment into our sector to consume less power so that in the end we consume less or burn less fossil fuel, and as a result we will have a reduced impact on the environment and improve our air and water quality. And then finally, there's just so much technology that's coming out continuously, advances in materials and electronics that are driving, enabling all kinds of solutions to give us the tools to create more efficient components within the system. So in the end, all these factors listed above are driving the design of energy-consuming devices to become part of a smarter system solution. And with that said, I'm going to hand it over to Matt, who is going to discuss commercial HVAC blower technology and trends.
Thanks for that, Dave. Hi, everybody. My name is Matthew Turner. I'm a design engineer working for Regal. So yeah, thanks for that, Dave, for running us through those, give us an overview of all the drivers involved with change. So I think what I got out of what Dave said is that the majority of change focuses around efficiency. And I'm going to run you through a description of blowers that sort of describes the evolution of this efficiency and how it's changed these air handlers. So the first one I'm going to go through is a belt-driven forward curved system. Then we jump to a backward curved system, so belt-driven backward curved, and then onto the direct drive backward curved. So I'll move to the next slide, please. Okay, so I'm going to go through the details of this forward curved blower system. You can see there's two examples on the left there. The top one's probably above 15 horsepower, and the one at the bottom is probably 1 to 2 horsepower, or something like that. You can see here I've chosen to explain systems with belt drives, and at the top there you've got looks like a 5-to-1 reduction ratio driving that, and the bottom one you can see a 1-to-1 ratio. When we look at these kind of blowers with belt systems where we take it for granted that we have to service these, and I guess that's something that we really have addressed when we're looking at this application and trying to develop something game-changing. So the other thing I'll describe is the efficiency. So typically a forward curved blower system is on the lower side, 60% efficiency. When you've got a belt system like this, we take an efficiency hit there. The other limitation we find is that they have to be in a housing, and when you have to be in a housing, the scroll to gather pressure off the backward curved blade, we actually get some efficiency hits. We take an efficiency hit in the system. So I look at this and I wonder why we use these in the first place, and that's an interesting point. So the features, the characteristics of a forward curved blower are actually quite flexible. The operating envelope of a forward curved blower allows you to run at a constant speed and service a bunch of different systems. So when you look at it in detail, you actually see that these blowers have been designed to run at a constant speed to keep an induction motor happy. So I'll at that point I'll move to the next slide, slide 10. So now we do an efficiency leap to the forward curve, to the backward curved wheel. So we're still keeping it in the housing, and we get a huge efficiency benefit, and we're up to 75% now. So the efficiency we're looking at here is between exactly at the outlet and exactly at the inlet of this blower. So it's a very micro view on the whole system, and we actually do get a good efficiency benefit. So we're also displaying a version that is belt driven as well. So we end up with those belt packaging issues and the efficiency hit. So I'll ask that question again of why weren't these used, and the other interesting thing is that they are very limited. When you've got a constant speed, your fan system efficiency is very peaky. So when you have to operate in a system that is off the efficiency peak of these motors, the actual efficiency can drop off, and that actually affects your induction motor and how it runs. So very quickly your efficiency can drop off if you're running in a bad system point. So I'll move to the next slide, please. So now we do another big leap, which is quite obvious really, when we take away the belt and pulley system and we drive the fan directly. So the other not so obvious leap is that a backward curve fan characteristic allows us to remove the blower housing. So we no longer need a housing to gather pressure off the blade and pressurize the system. These are very good for pressurizing a plenum or a box, and you would have heard plenum fans being used more and more these days. So let's look at that fan efficiency. The efficiency, when we look at the inlet and outlet efficiency, we've actually dropped efficiency because we're not using a scroll to gather pressure. But we'll see later on that you actually gain some system benefits in efficiency later. We get the obvious benefit of not having a hit from the belt system, so we're going direct drive, and we don't have those quality packaging issues and servicing issues with a belt-driven system. So the other interesting thing is it's not exactly the same as a housed backward curved wheel. These wheels are slightly different, and they're designed to go in and pressurize a plenum or a box. The last point I want to make there is this packaging size. So we're still using bare shaft off-the-shelf motors, and this limits us with packaging size and weight. So we'll address that in the next few slides. So I'll move to the next slide. So this is where I can summarize the efficiencies that I've just described. So on the left there, we standardize on a motor efficiency. You can see there that we take out the belt system efficiency hit, and you can see the fan system efficiencies. So this is where I could point out the system effects. So with our forward curved blower and the other housed blower, we end up with high velocity pressure. And when you're trying to pressurize a system, we actually have to put a diffuser there, and you actually get a pressure drop across the diffuser and an efficiency hit there. So you may think you're putting in a more efficient blower, but you're actually losing it when you look at the bigger system. So you can see we've doubled the efficiency just stepping through these designs here. So the other thing this plenum fan or the direct drive fan enables is the ability to stack these. So I'll move to the next slide. So we're kind of going full circle here, where we look at the forward curve blower, and we see that they were very useful to cover a big range of systems, but we had a big efficiency hit. So now we're kind of coming full circle where we can develop something called like a fan array or fan wall or fan matrix, and this allows us to have the flexibility to drive lots of different varying systems, because we can multiply the units, how many we're using, but we also get to have the efficiency benefits, and there are some other packaging benefits as well. So this is a solution that is the highest efficiency. We get the improved air distribution, so we get to pressurize a box or a room, and it works very well if you want it for upstream or downstream components with filters and things like that. So the other benefit, which I guess is quite obvious, is reliability and redundancy. When you have more than one unit, one can go down, or you can replace it whilst your system still operates. So to get the good advantage or the best advantage from a fan wall, we need to talk about the shift from induction motors to variable speed permanent magnet motors. And at this point, I'll hand it back to Dave to describe some permanent magnet benefits. Go ahead, Dave.
Thanks, Matt. Okay, so motor attributes. How does high efficiency flow down to motor design? So as we spoke about earlier, we've got a lot of drivers that are asking for increased system efficiency. And as we are, as Matt said, we're motor people. We're not necessarily blower people or HVAC system people. So we look at it as how can we improve the motor to achieve the higher system efficiency. And we know that we've got some advanced permanent magnet motor technologies that work very nicely with these sorts of applications, and in particular permanent magnet AC. Permanent magnet AC is very efficient, and it's great for running efficiency, but the downside of permanent magnet AC is that it cannot start itself across the line. So we need some sort of control or drive to operate that motor, to bring it up to speed and to run it. And that's where we introduce another package which we need to develop along with the PM motor, which is the power electronic control. And that power electronic control will contain microprocessors. So once we have those on board, we can do a lot of other very interesting and very technologically advanced things like having serial communication with the outside world. We can monitor system variables, monitor motor health and diagnostics, and that's becoming a very warranted trend. In addition to motor technology, we want to think of how can we integrate that motor into the system in such a way that we maximize the efficiency of the system and also provide a package that provides the least amount of loss in the system. And what I mean by that is that we want to provide a motor package that doesn't create any static pressure drops in the airflow stream. We want it to package nicely with the blower so that it sits off to the side and enables the blower to be the most efficient that it can be. Variable speed, of course, is there so that we can take advantage of the affinity laws of the fan to operate in the most efficient fashion, and I'll touch on that a little bit later. So Matt alluded to the differences between variable speed AC induction motor versus variable speed permanent magnet. And well, the AC induction motor starts off at a disadvantage to permanent magnet because, number one, it has rotor losses. It operates with slip. In order for it to operate, the rotor must operate or run at a slightly lower speed than the synchronous speed of the AC line. And so that creates currents and resultant losses in the rotor and additional heat. And then secondly, the induction motor has to obtain its magnetization energy from the AC supply line. So that's another form of loss that has to flow through the motor. Permanent magnet technology, on the other hand, has a permanent source of magnetic flux in the machine, which is created by the alignment of magnetic domains in those permanent magnets. And if we use premium efficiency magnets, we can create that field excitation with very thin magnet segments, which enable us to make the motor thinner, create more efficient flux paths within the motor, and so on. And so the permanent magnet machine has a higher torque density as a result than the AC induction machine. And then very importantly as well, the characteristics shown in the curve here, that not only does it have a higher intrinsic efficiency than the induction motor. The green is the PM and the red is the induction motor. The permanent magnet has an extended high efficiency region of operation, so it can run a much broader speed range while still maintaining efficiency. And so this is important to us in the way we can provide solutions to the blower designers. We can offer solutions with a need for far fewer motors than has been historical in the past. So in this plot, we're showing on the horizontal axis speed. The vertical axis is power. The dotted lines represent the system curves of a particular application, and the colored regions represent the areas of operation of 3 different motors. And so if you note the motor C, which is the smallest of the 3 motors, you'll note that it only goes up to about 7.5 horsepower at its peak. Can operate from over 5,000 RPM down to 2,000, theoretically down to 0, but probably the usable range might be 2 or 2.5, 3 to 1 in most applications. But because the motor has, if you remember the previous slide, such a flat efficiency curve versus speed, it can be used over a very broad region of applicability. Now, the straight lines coming out of the origin represent the torque limit, the continuous torque limit of that motor, or basically how high a value of horsepower it can run before it reaches its thermal limit. So that is going to be the limitation for each of these motors. Motor C reaches its limit, and then motor B becomes the next selection point if the system curve requires a higher degree of air power. I mentioned earlier about this, the desirability to run at variable speed. So how can I maximize blower motor efficiency? Well, in addition to starting with an efficient motor, one very powerful way of increasing blower motor efficiency is to, I guess you'd say, exploit the affinity laws of a fan. And those affinity laws will tell us that if we look at the plot once again, we've got relative speed from 0 to 1 on the horizontal axis, and let's just take flow, for instance, on the vertical axis. So the black line represents the amount of airflow, and you can see it's proportional to speed. Second affinity law tells us that static pressure in the system is going to be proportional to the speed squared. And so that is the red line that we see here, and it's got a square function. And then finally, the power that is required by the blower to produce the airflow that we want is going to be proportional to the cubic power of the speed. So without getting too technical, I mean, giving an example, I think will sort of highlight the power of these affinity laws. So say we're running our system at a relative speed of 1 at 100% power, and we realize that we only need 90% of the flow that we're currently getting, so we drop our flow by 10%. We're now running at 90% of our original speed, and if we go up and look at our power curve, we've now reduced power by almost 30%, which is a very significant reduction in power. So we've achieved a 10% reduction in airflow by simply slowing down the motor. Another way of potentially achieving the same effect would be to use a constant speed motor, which is kind of the older technology. But
then we roll to permanent magnet AC motors plus a VFD. These come in a variety of standard frame sizes, and you can typically get them to fit your system. So I'll jump straight through to the breakthrough technology that we're talking about here today, and I'll jump to the next slide, please. So now we're on slide 19. So far we've talked about the drivers for change, we've talked about fan designs, and now we've talked about permanent magnet variable speed motors. So now we can get together to to open up this breakthrough technology. So what you can do here is we float the design of the motor, and we design to a system to fit the application. So on the left-hand side there, you can see we've got a VFD, a permanent magnet motor, and then a backward curve fan at the bottom there. So together we get to, we're on the next slide, slide 19. So when we open this up, we get to create a system that is better suited to the applications. So I'll move to the next slide, slide 20. So when we end up with an ideal integrated solution, I've got this slide to tie back into the air handlers that I described before. We end up with a system that has the highest system efficiency. We have no belt drive efficiency hit. We have no packaging issues from the belt drive. We get the good pressure capability from the backward curve fan. And we end up with the smallest packaging and the lightest weight. And this enables the creation of fan walls much better. And we're really talking about a simpler product. So I'll move to the next slide, slide 21, and go through these features. So when we integrate the motor, we get to take away all the constraints that you have when you're developing a bare shaft NEMA style PM motor. We get to really broaden the the form factor envelope that we work in, and we really get to address the needs of the application. So we can minimize the weight of the motor and the packaging size when we float this form factor I've just described. The next benefit we get is the integrated drive. So when we integrate the drive, we get to eliminate drive setup issues. So if you've ever had to set up a VFD with a permanent magnet motor, it's not super easy. First, you've got the purchasing decision of what VFD you drive, or what VFD you purchase to drive what motor, and you've got to make sure they can talk to each other and then operate efficiently. The other thing it does is simplify the electrical installation. So without having a separate tethered drive, you only have to deal with one component. It simplifies communication. So when we get to develop the VFD integrated into the drive, we get to simplify the communications and develop communications specific for the application. And the other thing is reliability and serviceability. So typically these are more reliable products when the drive isn't an unknown drive driving a certain motor. We know that it's been set up correctly and nothing has been, I guess, set up incorrectly. Also, it's more serviceable. So the next bit is when we integrate the fan into the system. So when we do this, we really get to maximize the benefits when we develop a motor for the system. So we talked about floating the form factor, not to compromise any airflow. You can develop a system that is not increasing restrictions and things like that. So the point at the bottom here I want to talk about the most, and that is it's very difficult to make a system like this if you're a fan manufacturer. So there are systems on the market now where you can purchase the motor and the fan in one package, but if you're a fan manufacturer and you don't do motors, this is almost an impossibility to get to this point. So that's when it gets a little bit more exciting. I'll jump to the next slide, and we get to introduce to you a key ingredient to a plenum fan manufacturer, where we enable them to create a product range that is integrated. That we think will supersede any of the products, integrated products on the market today. So I'll go through all of those features again specific to this solution. So I'm introducing the UlteMAXT product from Marathon. This is a motor that's specifically designed to integrate into fan plenums. You can see there, I talked about form function. We've managed to design a motor that is, up to 15 horsepower that is only 5.5 inches thick. So we think that is game-changing technology. So we get to minimize weight for ease of installation. We get to minimize size so you can maximize space envelope to work with in your product and to shrink it if you need to. I'll jump to the next slide, slide 23. So Dave talked about the large operating envelope of PM motors. So we've developed a range of PM motors that allow flexibility for you to develop an integrated fan system. We've got three motor designs at the moment, and that covers the range from low speed 15 horsepower, so we're operating at 15 horsepower at about 1500 RPM, all the way through to high speed, maybe 5,500 RPM. So the other thing to note is this range of motors is extremely capable. So we not only can we deliver the high power, we can actually push speeds higher. So one thing I didn't talk about earlier in fan designs is the actual backward curve fan design themselves. So they're actually moving along as well, where they're getting stronger and they can spin them faster. So when you go faster, you can go more power dense. So our offering here with a motor actually enables future proofing for any sort of advancements in speed of the fan design. So the other thing we've done is develop this in one frame size, because the packaging of our 15 horsepower is relatively small in compared to what's in the market these days. We've standardized on a frame size to allow fan manufacturers to simplify the development of their range. So I'll move to the next slide, please. Slide 24. So I'd love to talk about this all day, but just a bit more detail on the features of this motor when we get to maximize the efficiency of the fan that we bolt onto. So you can see there, because we worked hard to make this motor thin, we can bolt onto the back of a fan wheel. So if you look in the center photo here, that grey blob on the left-hand side is our motor, and you can see we don't protrude into the airflow of the fan itself. This allows the fan to operate at full performance without any sort of restrictions induced by the motor itself. Also, keeping it thin allows us to keep that package short and maximize the space available in your air handling unit, or at least reduce the size of the air handling unit. So the photograph on the left there, which you've seen a few times now, is the motor itself, and you might be wondering why there's so many fins on there. And even though this motor has an ultra high efficiency, we're talking 96% motor efficiency, because the packaging is so small and we squeeze it in such a small place, we still have to get rid of some of that heat. And I guess we're passively cooling it with the application fan. So we like to put the fins there so we can get rid of this heat, so we can operate in a very large range of application scenarios. You can see on the right, got a very basic picture of some CFD. So underneath all those red lines there is the motor itself. And this just shows in application how the motor is cooled. In this scenario, the exhausting air comes out from the fan, and we actually get a column of air heading straight in towards the center of our motor. And then that passes out and back into the exhausting air. And this, like I said, I could talk about it for ages, but this is just a basic view of how we're cooling this motor in application. Okay, so I'll move to the next slide. So I'll briefly talk about the drive, and then I'll hand over to Dave. But so this is a really basic exploded view of the product. You can see in the center there we have the mainframe that I described. We have the three motor sizes there to cover the broad range, operating range. On the left-hand side, we've got the inverter pod, and on the right-hand side, the rectifier pod. These two components make up the drive, typically known as the VFD, I guess. These have been designed specifically for operating the motor, so they've been optimized, and also packaging size is reduced. The pod on the top is the user interface, and I'll let Dave talk about that a bit more. And I'll go through the points here when we integrate that drive. So we get to eliminate those drive concerns when you have a VFD you want to set up with your PM, a tethered drive to a PM motor. Simplify the electrical installation, simplify communication, and the last point here is the reliability. So you might be wondering why we've separated it into 3 pods, and that is not because they're going to fail, because we are very good at making reliable electronics. But one of the things we've addressed in our looking at the application is the serviceability of the pods, the drive. So we have the ability to come in and swap out a drive if it fails, which it won't. So I'll move to the next slide and hand over to Dave to talk about more of the electronics.
Okay, Matt. I'm actually going to stay on the same slide for just a bit and just expound a little bit on the pods themselves. A great deal of thought went into the segregation of the functions of the drive and into the pods. And what's happened as a result is that the drive system is very scalable. So as you might imagine, the contents of these pods change when we go from 3 horsepower at 230 volt to 15 horsepower at 460 volt. And we were able to modularize that and thus make that package very scalable while still maintaining the same mechanical housings for those, so that you can count on that mechanical package maintaining a fairly consistent form factor. The other nice thing about that, Matt mentioned a really great phrase called, I think, something about future compatibility or future proofing, and I think this arrangement gives us a good future proofing attribute to the product. In addition, I think we're in a good position to provide users, different users with possibly unique interface pods depending on what their needs are. I'll expound on that a little bit here with the next slide. Thank you. Okay, so here we have a user interface pod, and I'll just go briefly through the features of it. Let's start in the lower left-hand corner. We have a dip switch array for setting motor direction of rotation and also for setting a motor address in the event that we want to have a multi-drop serial communication bus protocol. And speaking of that, we have an RS-45 port with a Class 2 10-volt power supply. Class 2 meaning that that is fed from a doubly insulated transformer secondary to provide the UL required level of safety. We've got analog and discrete speed inputs where we can feed in either a 0 to 10 volt speed signal or use digital lines to feed in discrete set points of speed. We have a fault annunciation relay, and then as we jump over that barrier there's a barrier between the low voltage control side of the pod and the high voltage power input side of the pod. And in the power input side, we have a grounding screw and a three-phase terminal block that can accommodate up to 10 gauge for our 15 horsepower package, and using the spring cage type positive locking terminal blocks. So as I mentioned in the earlier slide, this design is very flexible because of the modular approach to it. So our question to you is, what do you need for your interface? Because this is something that we can provide a lot of custom offerings depending on your needs. So tagline here being maximum value and maximum payback to your bottom line. And I think that finishes our portion, Matt's portion, and my portion of the presentation. So we're going to hand it back to Jason to bring it to conclusion.
Thanks, Matt. Thanks, Dave, for explaining. So I promised there wouldn't be a test, or I said there might not be a test, but I would like us to go back and look at the 4 takeaways from today and make sure that we captured these. So identified the key drivers for change in the HVAC air handling units. Dave identified it for me when he said that we use $71 billion of electricity to drive these things. And if we can do a 1-point-something% efficiency improvement that meant $1 billion in our pockets, that's really important to the people paying the bills on these motors when they're running on the roof. Understand the HVAC air handling unit shift to integrated motor fans. So Matt went over the belt drives and the efficiency of the different types of motors, different types of fans, different types of systems. And I think, clearly understood that the belt efficiency was a bit of an issue there, and that's why the integrated fan is important. Need to move the PM motors and variable speed. There, Dave explained how the affinity law works to our benefit with the variable speed, and how the flat efficiency top, the broad speed range that a PM motor stays efficient, is beneficial. So that's the need for PM and variable speed. And then how to enable a better HVAC product with integrated fan motor. That's what we wanted to do. So when we took the piece of paper and we started looking at this and figuring out what this product should look like, believe us, we started with something that looked much like what we do today. And we realized that if we want to do it better, we have to do it different, and we've got to do it different for a reason. So we came up with a solution that's better and different. It solves a lot of value questions at every level and offers a lot of better design, a lot better design without much compromise at all. So with that, I'd like to, first of all, thank you for attending. And the second thing I'd like to do is invite you to visit our booth. If you're going to be at the HR show in Las Vegas, visit our booth. We'll be at 3318C, Center Hall, booth 3318. While Vegas is full of tricks and illusions, there isn't a lot of illusion behind these benefits, and we'd really like you to come and see it in person and talk to Matt, Dave, and I in person at AHR and really, ask the questions and understand it. So with this webinar now, we'd like to go ahead and answer a couple of questions. Darryl?
Great. Thank you very much, Jason, and thanks to David and Matthew for their presentation. As promised, we're going to go through and answer some of your questions that came in throughout the program. So our first question is from Asif. I hope I'm pronouncing that right. He's asking, is there a limitation, suggestion, or other considerations for the number of fans that can be grouped to operate with a single VFD?
I guess, I'm sorry. This is Dave. I'll take a shot at that question. Being that wasn't really the topic of today, but I understand that is a common solution in the field to operate a large number of fans off of a single VFD. And I guess that's more of a question for a commercial variable speed drive manufacturer. But in our case, we have individual VFDs on every motor, which can be communicated to through a serial bus. So I think the advantages you have there, and I know that's not, I'm getting off the question a little bit, but I think the advantages that you have there are that each motor is protected individually. rather than having a large number of small motors running off of a large VFD. If something happens to one of those small motors, an overload condition or something, that may not be enough signal for that drive to recognize it as a fault because it's driving a whole lot of motors and it's not sensitive enough to see a problem with one motor.
Okay.
Yeah, I could add to that. I guess in what aspect are they interested in multiplying? So
yeah, I think the general question about running multiple motors on a VFD, when we go into permanent magnet type motors, while there are some people making headway in running multiple permanent magnet AC motors on a single drive, it's not common practice yet. That's mostly happening in university and research projects within companies. So as you go to PM technology, it does require a unique drive or a single drive for each motor. So that's one of the primary reasons and exciting parts about the technology. With the integrated drive, it's matched perfectly to that motor.
Okay. Our next question is, does this product solve the assumed pending regulations for commercial fans that are coming out?
Yeah, so the assumed pending regulations really require us to start to look at system efficiencies. And we've designed this motor with system efficiencies in mind from the very beginning. So as Matt laid out and as Dave laid out, the efficiencies of the motor and the efficiencies of the different type of fan designs, system efficiency was a primary driver of consideration. Variable speed is what we believe the pending regulations, the upcoming regulations will demand, that motors that are driving fans be variable speed. So this in itself being a variable speed type motor, and then further an ECM type motor, a permanent magnet ECM type motor, we believe satisfies the requirements of that. Now, Regal is constantly watching the regulations that are coming, and we stay ahead of those. So we will be monitoring those to make sure that we have a solution that works.
Okay. Next question is from Jeremy. He says, what is the voltage range for the product? His assumption is the VFD is adaptable to 3 or 4 major input voltages?
The VFD currently is offered in 2 voltages, 230 volts and 460. Well, line voltages would be 240 and 480. Nameplate voltages on the motor would be 230 and 460. These are the most common commercial voltages out there. Both of them would be 3-phase ratings. It's the 3 and 5 horsepower models that are offered in 230 or 460, and then at 10 horsepower and up, it's 460 only. We're working on also getting ratings for the counterparts in the 50 hertz European standard voltages.
Okay. Our next question, would the components of the integrated motor drive system be sensitive to the presence of humidifiers upstream of the fan section?
We go through a very rigorous set of design verification tests, and one of them is a humidity test, a 500-hour humidity test. And so we are very confident that the product will operate in the presence of humidity.
Okay. Looks like we've got maybe time for a couple more here. So next question is, does this axial motor have the technology to mitigate bearing currents?
So I could answer that one. So in axial technology in general, does have the ability to mitigate the problem of bearing currents. In this motor in particular, we have reduced it, but we've also introduced a component to completely get rid of it, which is like a grounding brush for the shaft. So there are other products which are axial, where we get rid of bearing currents without the addition of any components. But just to be sure, with this product, we have actually added a component to ground those bearings.
Okay. Bob would like to know, are there other communication options available in addition to the RS-485?
At the present time, there are not. But as mentioned earlier, the product is very adaptable, and that's certainly something we would love to have a discussion with Bob about.
Okay, great.
Yes.
Great. Okay, again, looks like we have time for one more question. So what's the technology difference between EBM's motor and the new Regal motor?
Well, the primary technology difference is the way that we transmit the flux through the stator. So we're using what's called an axial flux type of a machine instead of a radial flux type of a machine. So radial flux motors are what you would think of today, the common motors of today. So a drum rotating inside of another drum. Axial flux motors are two plates rotating against each other. So you have a plate with magnets on it and a plate that's got coils on it. The plate with coils is stationary, that's our stator, and the plate with magnets on it is our rotor. So that technology is what enables us to mount directly to the fan wheel and not, because it's a very flat sort of platform, not intrude into the inlet of the blower. So when we have a fan wheel and we do a typical radial type of a machine, to maintain the same axial length, the overall length of the packaged unit, the radial machines have to be pushed inside of the inlet of the wheel. So it's the axial versus radial technology that's the primary driver between EBM and Regal's solution.
Okay, great. Again, looks like that we're just about out of time. So this concludes today's webinar. So please join me in thanking today's presenters, as well as our sponsor, Regal, featuring Marathon Motors' latest product edition, the UlteMAXT motors. As you exit today's webinar, please take a couple of minutes to complete our survey by clicking on the survey icon in the taskbar. We strongly welcome your detailed comments to help us serve you better. If you have any additional questions or comments, please don't hesitate to contact webinars@bnpmedia.com. We appreciate your time and hope you found this webinar to be a valuable experience. Have a great day.